My goal today is to build a language model that knows the rules of touch rugby. It's a good choice because touch rugby is a fun but a somewhat obscure sport. There's not a lot of information online, and so models like Llama don't really know the rules that well. That gives us a nice base for comparing performance when we use an embeddings approach and a fine-tuning approach. Today we'll be focused on the embeddings approach to answer questions about the rules of touch rugby. You're probably used to using Control F and searching for words, but embeddings allow us to search for meaning rather than just directly search for words or phrases. With embeddings, we represent the question by an arrow. We also take the document and we represent each paragraph or phrase by an arrow. And the direction of these arrows is representative of the meaning. So the whole idea of embeddings is to find the closest arrows. We have an arrow for a question like how many players are on a touch rugby team, and then we have many arrows representing paragraphs in the rule book. And we look for the arrows that are pointed in a similar direction. For example, teams are made of 14 players with a max of 6 on the field. And by grabbing those snippets whose arrows are similar in direction to the search term, we can grab relevant context. Now, how do we get these arrows and where do these embeddings come from? They come from the very first layer of a language model. A transformer architecture like is used with GPT-4 or Llama has very many layers, but the first layer is responsible for converting the original tokens into an arrow representation. It's a vector representation in high dimensional space where the direction roughly corresponds to the meaning and content of that phrase. Now, the embeddings happen on a token by token basis. So you have a little arrow for every single token. But if you want an arrow for a phrase, one approach is simply to average across the tokens in that phrase. So you average the smaller arrows to get one arrow for that phrase. How can we make use of embeddings if we want to answer questions about touch rugby? Well, our standard approach is to just ask the question, how many players are on a team? And Llama won't fare very well with this because Llama is not familiar with the rules of touch rugby. But how about if we use a search for meaning to find the most relevant pieces in the rule book and feed them into Llama? For example, we can say how many players are on a team, make use of the following info. And then using an embedding search in the rule book, we can pull out paragraphs that we think are relevant and insert them here as useful info. This will greatly improve the performance of Llama because it's providing relevant context. Now, there are two keys to success in getting embeddings to work for the rules of touch rugby or for any of your use cases. You need to have a good embedding model, meaning you need a good way to calculate the arrows and make sure that you're finding the closest arrows. The second thing you need is a good language model. Even if you give the correct information to a language model, it still might make mistakes. We're going to see that Llama, even when you feed the right embeddings, can sometimes just hallucinate. Even GPT-4 makes mistakes, and I'll show you a few of those too. The key point is you got to distinguish between two aspects of performance. One is the performance of embeddings. Are you retrieving enough information and the correct information to answer the question? And two, is your model strong enough to be able to parse that information into the correct answer? Before we wrap up, I want to mention one more point, which is around measuring the closeness of the arrows. Broadly speaking, there are two approaches to doing this. The first is a cosine approach, which literally measures the angle between the search vector and the closest vectors within the document. This is good if you want to measure the closeness of content of those two arrows. However, it doesn't tell you anything about the amount of content. For example, a short paragraph might talk a lot about the number of players on a team, whereas a long paragraph might go into greater detail. And generally, we do want that detail, which makes it more useful to use what's called the dot product. The dot product is a projection of one vector upon another, and it tells us not just about the angle between the two, but also about the quantity of information. So if we're just interested in type of info and we have a short query looking for short responses, we'd use cosine. But if we have a short query and we're looking to extract larger chunks of text, it's better to use dot product, and that tends to perform better too. So that's what we'll use. The dataset we're going to use for training, for fine-tuning in part 2, and for our embeddings here in part 1 this video are the official Touch Rugby rules. I've gone online and found these rules. There are about 24 pages of rules. I'm going to download the file and save it as train.pdf. Throughout this video, I'll be making use of the Trellis Research Llama fine-tuning repository. You can purchase access to the repo or to individual scripts in the description below, but I'll try to describe everything in this video so you could just replicate it all from scratch yourself. Here we have an embedding notebook. I'll be using this for running the embeddings and also running the language model. But first, we need to prepare some data on the rules of Touch Rugby. For that, I'll be moving to this data prep branch, which has some scripts for preparing the data. So let's get started. Okay, I've just cloned the repository, Llama fine-tuning. I've activated the virtual environment, and now I'm going to do git switch into the data prep branch so we can start with data preparation. You'll see a data folder and there's train.pdf, so I've put the training PDF in here, and now I want to convert this into text, so I'm going to run Python PDF to text txt.py, and that's telling me that it's converted the train.pdf to train.txt. I didn't provide a text PDF, so test PDF for validation, so it's not converting that. So here we have in text form a copy of all of these rules. Now for embeddings, I want to split this into chunks, and then each of those chunks I need to convert into a vector or an arrow. To do that, I'm going to run create dataset, which is going to split it into chunks. I'll be able to choose when I run the script the size of those chunks. And here I have to specify the overlap. So what I'm going to do is run with an overlap of 50. That means that instead of just chunking it, it's going to have an overlap in the chunks. And basically what that means is if you have situations where there's a run over sentence, then you're not going to have a cut in the data set whereby there's no single chunk that covers what's overlapping that split. So we'll use an overlap of 50 tokens here, and then I'll run Python and I'll say create dataset.py. Now I'm being asked to enter the number of tokens for each data row, so I'm going to do 100. So I'm cutting it into chunks of 100. Now the last step is I'm going to make this dataset available online, which is not absolutely necessary, but you'll see it's nice because you'll be able to replicate as well in your own time. So for this I'll run Python push to hub.py, and I just made a mistake there. Python push to hub, and it's not push to hub, it's push to hf.py. So it's asking me for my Hugging Face token, which I'm going to grab it from here. So copy that token and paste it in. And I'm going to enter the path that I want to push this data set to on Hugging Face. Now I've created a data set manually, I've created a repo manually on Hugging Face, and the repo is trellis/touch rugby rules-embeddings. Okay, so it's now uploading, and now I should be able to view that data set here. So I have a data set which I've called train, although it's really just a vector, well, not yet vector, but it's just a data set containing the snippets. So you can see here my data set is being split into 48 rows. So I've represented those rules as 48 rows that each have 100 tokens with an overlap of 50 tokens. So at this point, I've just created a data set from the rules. I've basically created these snippets of 100 tokens long. And you might ask, well, why 100 tokens? And it depends. You can play around with what works well. But the basic logic is that if you make the snippets too short, then when you're searching for the right arrow, it may not have enough information to deem itself relevant, particularly if there's a snippet where there might be a relevant word at the start and the end. If your snippet size is smaller than that, you're never going to find an arrow that contains those two pieces of information. So you need to be long enough to cover what you think is a typical relevant snippet to answer your question. Typically that lands in the range of maybe 200 to 500 tokens in length. If you start making it really long, now the arrow is going to represent a lot of information, and so it's going to be more of an average over all that information, which means that when you compare your search term, it's going to be more, let's say, washed out, less specific. You'll have an arrow with a question, but the information is so diffuse because it's such a long snippet, it might not recognize that it has some similar information. Dataset ready for the embeddings. We're going to open up a Colab notebook, which is going to allow us to run Llama first without the help of embeddings, and then with the help of injecting that extra information. So let's open up the Colab notebook. I'm going to be running using Llama 13B. The reason is because I'm using a free Colab notebook, and 13B is the largest model that I'm able to fit without overwhelming the memory. I could use the 7B model, it would be slightly faster, but I think it's worth using a little bit more of capability and running with 13B. I'm going to run the model in GPTQ quantized format. Quantized means it will run in 4-bit instead of 16. This makes the model a lot smaller at only a small loss in accuracy, and it allows us to run it in a free notebook. Since I'm running GPTQ using the blokes repository for the model, I don't need to log into Hugging Face because it's not a gated repository like Meta Llama if I downloaded the original Llama 2 model. However, I will connect my Google Drive by running all of these cells. The reason is that will download the model to my Google Drive so that I can be quicker to start up the next time around. You don't have to connect Google Drive, but it means you'll be downloading the weights from Hugging Face every time. Okay, Google Drive is now connected. And as I said, we're going to install GPTQ. It's a little bit faster than using bits and bytes and F4. In fact, it's quite a bit faster, maybe a tiny bit less accurate. Maybe it's hard to tell depending on the data set, but we'll run with GPTQ and I'll run the installation. Optionally, you could comment that out and run in bits and bytes and F4 here. After GPTQ is installed and the model is being loaded, we'll then load the data set. Here is the data set. It's just a link to what we previously showed here, the touch Rugby Rules embeddings. Now, just a reminder, this is not the embeddings, it's not the arrows, it's just the text snippets. We're going to be calculating the arrows in the Colab notebook. Moving on further, once we've loaded the data set, we are going to test the embeddings, but I'm going to come back to that because first, I just want to show you how the model runs if it doesn't have any help from embeddings. In other words, let's just get Llama to answer the touch rugby questions without any training, without any extra injected information. The way we'll evaluate performance throughout this tutorial on embeddings and the next on fine-tuning is by asking a series of questions about touch rugby that I myself made up manually. For example, how many players are on the field on each team in touch rugby? And the answer is 6 players. Now, we'll also provide a system message. I'll just scroll up here to find that. Saying, you are an expert on the rules of touch rugby. You provide succinct answers no longer than 10 words. So this is the test case on which we'll evaluate Llama Performance. And it's also how we'll evaluate using embeddings and later using fine-tunings in the next video. The GPTQ model now has been downloaded. In fact, I downloaded it earlier to Google Drive, so it was quite quick. And I only needed to reload the shards. The tokenizer has also been downloaded as well, which means that we're ready to run now a test without the embeddings. So I'm going to set up my test function here, and then I'm going to evaluate without the embeddings. So I'm saying use embeddings equals false, which means I'm not injecting any extra information. So here's the first question. How many players are on the field in touch rugby? We have a warning here, 6 players per team. So Llama does seem to know the first question. Does a forward pass result in a roll ball, a scrum, or something else? Llama says a roll ball, which is incorrect. It's a penalty. How many meters does a defending team retreat? 5. That's wrong. It's 7. How many substitutions are allowed? There's no limit, but Llama says 3. How long is half time? 5 minutes. It gets it correct. How's the game start? A kickoff. That's wrong. It's a tap. How far do you retreat for a penalty? 10 meters. How many touches before turnover? It's 6, but Llama says 3. What happens if the player is touched before making a pass? There's a scrum. There's no scrums in touch rugby. And lastly, how many points for a try? It's only 1 in touch rugby. It's 5 in normal rugby. So Llama, just raw without any embeddings, gets a score of 3 out of 10. Depending on the size of Llama, it actually doesn't change that much. I think it's usually 2 or 3. Even I ran the 70B model and it still gets 2 or 3. So Llama probably has a pretty good understanding of rugby, but touch rugby is a bit obscure and only scores about 2 or 3. So that's the baseline we're trying to improve on by injecting extra information. We're now going to move to inject embeddings within the prompt to improve the quality of response we get from Llama. The first thing to do when we set up embeddings is to check that when we ask one question, does it retrieve relevant paragraphs that will help us answering that question? Now, there are 3 different ways that I'm offering here for calculating the embeddings: Llama embeddings, OpenAI embeddings, and Marco embeddings. Llama embeddings are simply using the first layer of that language model. And this is a pretty easy way to use. You don't have to download anything else since we've already loaded the Llama model. So this is quite a quick script if you do want to use those Llama embeddings. You can also use the OpenAI embeddings, which means sending each snippet of text over to OpenAI, and they will respond an arrow for each of those snippet of text. Now, this is a bit trickier because I'm rate limited to 3 calls per minute, which makes it very slow to get all the embeddings, although I could request access for higher rate limit. Plus, I have to pay for each embedding here. So I tried this approach, and generally it didn't perform as well as some of the open source methods, or maybe it performed similarly. So I generally prefer using open source embeddings. And the open source embeddings I'm going to use here are what I'm calling Marco embeddings. These embeddings are available from this website here. It's the SBERT.net website, and it's a model that's been tuned for dot product. You'll remember in the intro, I described that either you can measure the angle between the search query and the document's paragraphs, or you can do the dot product, which also accounts for the amount of information. This MS Marco DistilBERT model has got the highest performance, and it's fine-tuned for dot product. I think that you probably would get some good performance with many of the other models here. So I'm not suggesting this is necessarily the best, but I think that it's a pretty good model, and I found it performs similarly to Llama, but much quicker and also without any cost. To use the embeddings, we need 2 things. We need a table of all the paragraphs, and we need a query. We've already created a table on Hugging Face of all the paragraphs from the rules. So we've imported that here by loading the dataset. And you can see that the very first row here of this training dataset contains a snippet that has 100 tokens. And there are 47 other rows like that. So we've basically imported into the data train variable here, we have imported a list of snippets that we are going to calculate arrows for. And we're going to use Marco to calculate those arrows. Let's scroll down here to Marco embeddings. We install sentence transformers, which is the package needed to access that model. And using that model, we're going to embed the full database. So this is what's happening here. We have the train embeddings. We have the data.train dataset, and we're running it through the Marco embedding process to calculate an arrow. So here we're calculating an arrow for each of the 48 rows of that training dataset. Then we're posing a test question. How many players on the team are on the field at one time in touch rugby? Here we're calculating an arrow for that question using the Marco approach. Now comes that dot product step. So we're taking a dot product between the question embedding and between the training embeddings, the train embeddings being the rules of touch rugby. And what this is doing is seeing what the dot product is between the Marco embedding, the Marco arrow, and each of the other arrows. And from there, we're going to pick out the top 3. So I've set n samples to 3. So I'm deciding that I want to take the 3 most relevant snippets and then I want to print them. So let's just run that very quickly, and we should get out a list. It has to download the model, download the tokenizer for that model. It's a very lightweight model relative to Llama, so that's why it's so fast. And here you can see it's found similarity scores, which are the dot products for each of these. And remember, our goal is to find the number of players. And you can see straight away that the most similar paragraph it's found is saying a team consists of 14 players, no more than 6 are allowed in the field at any time. So Marco is working very well here. The very first of the 3 embeddings that it's finding, or the first of the 3 arrows, is the one that we want. What we're going to do now is we're going to run through each of the 10 questions, and we're going to include embeddings within the prompts. So let me show you what that looks like. In addition to asking the question, if we turn embeddings on, if we turn on Marco embeddings, then we're going to inject the snippets in. So we're going to say, after asking the question, here are some snippets from the rules of touch rugby. And we're simply going to inject 3 of those snippets. And then we'll say, answer the following question succinctly, solely using the above snippets of text. So let's scroll down now. We've already evaluated the model without using embeddings. So let's now evaluate with the help of embeddings. And we're going to input the questions, the answers. We will use embeddings. I'm going to inject just 3, actually. I'll just inject 3 embeddings. If you inject more, you're giving more information. Generally, that will help if you have a strong model. If you have a weaker model, more information might confuse, because the more you include, since they're ranked, the less relevant the information will be. So on a weaker model, somewhat counterintuitively, putting in more information can make the answer worse. And then the embedding type we choose, you could set it to OpenAI. You need an API key for that, or you could set it to Llama, but we're going to use Marco. So let's run this evaluation here and see how it does. So in the first question, we have how many players in the field? 6. So it's getting that answer correct. The next question here, does a forward pass result in a roll ball, a scrum, or something else? And it says roll ball. So that's wrong. Now the question is it wrong because the language model is wrong, or is it wrong because the embeddings did a bad job of finding the right paragraph? And to answer that question, we can just highlight some of this here. So we'll take a highlight and we'll head over to ChatGPT, create a new chat, and just paste in that question. Let's see what ChatGPT comes up with. So here, forward pass is not mentioned. So you can see that actually this Marco was not successful in finding the right snippet for forward pass. So it's not really Llama's fault, it's the embedding model's fault in this case. Now moving on to the next question here. In touch rugby, how many meters can a defending team retreat? 7, so that's correct. And by the way, you can see that the question is posed in the following way. Here are some snippets from touch rugby, so it gives the relevant snippets, and then it asks the question here, how many substitutions in a game? So it says 8 substitute players allowed during a game. So that's correct. It's not answering the fact that you can make unlimited substitutions. So it's I'd say only partially correct, although I wouldn't be confident that GPT is going to be much better at answering that question. Yeah, so it also doesn't exactly answer the question. I guess maybe my question is poorly posed, but ask a follow-up question. Okay, well, that's correct. It doesn't specify. So you can see a bit of an edge case there. I don't think we can fault GPT too much. Let's move on to the next question here. Halftime is 5 minutes, so that's correct. Question 6, how does the game commence? It commences with a roll ball at the nearest point on the 7-meter line. That's incorrect. It starts with a tap on the halfway line. So what we can do is ask GPT here what it says. And GPT does get the correct answer. So here, you know that the embeddings are correct. So Marco is correct in finding the right information, but Llama is not able to parse the information properly. Let's move on to question 7. In touch rugby, how many meters must defenders retreat when there's a penalty? It's getting that wrong. It's actually flipped the penalty and it's flipped the difference between a penalty and a touch. So let's see if GPT would be able to get that right. Okay, interesting. So you can see here, it thinks that after the touch, it clearly says here that it must be 7 meters, and yet GPT and Llama both get confused and they flip around the order. So even a powerful language model here is just not getting the facts correct. And I think that really puts things in perspective. Let's continue here with question 8. How many touches is the team entitled to before change of possession? 6. And last question, second last question. What happens if the player's touched by an opponent prior to making a pass? That is a penalty, but it's getting the answer wrong. So let's see why. I'm putting it in here. And yeah, also GPT gets that answer wrong. And let's take a look at the data that was provided. Okay, this is a case where the embeddings model is being stretched, and also the language model is being stretched too. The embeddings model is stretched here because there is very similar text talking about when that ball is accidentally knocked from the hands of a player, and the touch counts in that case. And so this is kind of similar, and I can see why the embeddings is picking up this sentence, but there also is a sentence that relates to being touched right before a pass that it should be picking out, and it's not. And when you look at GPT's answer here, it's saying the touch counts and the attacking team retains possession, but that's not exactly the question that I asked. So GPT's weak reasoning on this question is also not 100%. For the last question here, how many points is there for a try? And the model gets it correct for 1 point. These 10 questions on touch rugby give us some really useful insights into the performance of embeddings and of Llama's performance and even of GPT-4's performance. To recap, we ran 10 questions through Llama 13b with no extra help, and it got about 2 or 3 out of 10 of those questions correct. When we added in embeddings, it brought up the number of correct answers to about 5 or 6 questions correct out of 10. The remaining questions, let's say 4 questions, were wrong for different reasons. In 1 or 2 cases, the embeddings model wasn't able to find the correct snippet and provide it as context. In 1 or 2 other cases, Llama's reasoning was not as strong as GPT-4's reasoning. The embeddings model had given the right information, but Llama drew the wrong conclusion. But interestingly, in 1 or 2 cases, we saw flaws as well in GPT-4's reasoning. Even though the correct information was provided by the Marco embeddings model, GPT-4 was not able to reach the correct answer. Before we wrap up, let me give you a few pro tips if you want to push performance a little further. We haven't fully optimized prompting, so you might be able to eke out some more performance with Llama and GPT-4. For example, you might ask the model to respond that it's unsure if there isn't enough information in the snippets. You might also ask the model to reason step by step. On a more technical note, we used a dot product approach with the Marco model. However, there are some other more detailed approaches like ColBERT. I want to give a shout out to the SVIC podcast, which is on YouTube channel as well, for this recommendation. But ColBERT is a slightly more advanced approach. I talked earlier how you can embed each word into a little arrow, and then you can average those words to get a large arrow for a sentence. However, another approach is you could individually compare those words with the query, and then you can take an average of the comparisons. Said a little differently, in the approach that I've taken and the standard approach, we're averaging the embeddings across the tokens, and then we're comparing that large arrow for a paragraph with the arrow for a query. But with the ColBERT approach, what you're doing is you're comparing smaller pieces of that paragraph with the query and then taking the average before deciding which paragraph to choose. And this allows you to keep a little bit more information and might lead to better results. Let's finish with a few tips. Remember, dot product generally performs better if you're searching with a query for large paragraphs than using cosine similarity. Consider using Marco or a similar free embedding database or model from SBERT. It's cheap, it's basically free, and often it will be faster because of the rate limits of OpenAI. As you know, bigger models do perform better. We saw how GPT-4 will get maybe one answer right more out of 10 in the case study we looked at today, but even GPT-4 can make mistakes. And it's important to separate the embedding performance, which is fetching the right pieces of text, from the language model performance, and figure out which part of your pipeline is working or not working. Last of all, remember that no model is perfect, and so I highly recommend writing out some manual examples and make sure to manually inspect the results you're getting from your model. That's it for part 1 on embeddings. I hope you'll be around for part 2 when it comes out, and we'll do the exact same thing to take a fine-tuning approach. Let's see how close we'll get with fine-tuning to 10 out of 10.